So, welcome to the course on FPGA based signal processing systems. Let's continue with this technology review. Here in the previous lecture, we had looked into the age of invention and then age of expansion. So, what were the major concerns, area efficient FPGAs, and there is a development in the architectural modules. The innovations in the architectures during the invention age. Also in the expansion age, the LUTs and the interconnects were growing, and the area was also a part of the concern, but there is a trade-off between this area performance and the ease of use. So, the design automation tools were part of the expansion age. So, the design automation tools developed like anything in the case of expansion age. So, when coming to the next age of FPGA evolution, so the age of accumulation, which is from the millennium 2000 to 2007. So, in that age, that is the again the capacity and the design size were growing. So, the logic blocks and the expansion age does not only belong to the expansion, the age of expansion. In the accumulation age also the capacity was growing and the design size were growing. So, according to the Moore's law. So, obviously the capacity should be doubled and the cost should be half. So, that the context of this dot-com bust, due to that the business failures, there is increased demand for low cost solutions. So, when the capacity was increasing and the size was trying to reduce the size of this FPGAs, and then so the low cost solutions were very difficult to get into because of those business failures due to this dot-com bust. The low cost solutions, especially there is a real shift in the market of the FPGAs. So, the market shift, the FPGAs of low end were absorbed more compared to the high end ones. So, the low cost FPGAs are coming to the market compared to this ASIC. So, the ASICs was replaced by the FPGAs. So, the FPGA is capturing the market of ASICs in this duration. That means that there is low end FPGAs. There were two types of FPGAs that have been manufactured. One is this low end one and then high end one. So, the low end FPGAs having the efficiency, but it has a lower capacity and lower performance and low cost. So, when we go for these things, the efficiency, still the efficiency is not compromised, but the whatever affordable the cost and the low performance were also incorporated in the low end FPGAs. So, these were low end FPGAs were popular. Also, the FPGAs which were introduced of low cost by the Xilinx was Spartan. So, the Spartan was this part of that in this era, that is in the accumulation age. So, and Altera also introduced that Cyclone FPGAs, and the Lattice EC and ECP FPGAs were introduced by the Lattice. So, these are the three low cost FPGAs by different vendors of Xilinx, Altera and Lattice. And coming in the same age, there were other type which is of high end FPGAs, the larger size FPGAs, also the spacious ones are coming to the market. In that case, this libraries of soft logics have been introduced. That is for the some important functions have been added or through the soft logic. That is, there some IPs were developed, that IPs are added into the FPGA as a feature in the accumulation age. So, also the microprocessor were attached to the FPGAs. That means that Xilinx has come up with a microblaze FPGA, and also Altera had that Neos processor. So, it is those were microprocessor based ones have been introduced with the FPGAs. So, it will contain these processors as well. So, the communication protocols also included in the FPGAs, because and then the memory controllers also part of the accumulation age. So, adding different blocks to the FPGAs were the main concern in the accumulation age. So, because of the protocols, communication protocols were introduced, and there were interfaces. There is a need for standardization of the communication protocols, and the interfaces needs to be integrated to the FPGAs. So these needs standard interfaces, and because of the soft logic IPs also needed the standard interfaces. So these were included in the accumulation age of the FPGAs, which demanded again the additional LUT. So when we go for the standard interfaces and the soft logic, so the logic blocks again increased. So the LUTs were increased more in the FPGAs. So the growing concerned how this FPGAs were growing also in the case of computation intensive applications. The target was that computation intensive applications, the FPGAs were developed by incorporating computation intensive modules to it. So the soft logic and the microprocessor, microcontrollers, and the demand of these standard interfaces made that additional LUTs, also the computational intensive modules have been introduced in the FPGAs through the soft logic. Apart from the soft logic IPs, there is a dedicated blocks. So the dedicated blocks were the ones because of the standards. So the standards also again which were introduced in the accumulation age, so which decreased there is a need for decrease in cost, also power. These are the attributes of FPGA devices mainly. So while introducing or meeting out the demands of standards, the cost and power needs to be reduced, which led to the shift in the architecture again. So that shift in architecture in the sense it's not only logic blocks and the LUTs, the dedicated blocks were added to the FPGAs. So that's the main concern of the accumulation age. So the larger memories were introduced. So the LUTs of the larger memories, and there are multipliers which are very much useful in the case of DSP algorithms deployment. So for the filter designs, and we need the multipliers, so the 14-bit multipliers or the 16-bit multipliers. So 12-bit multipliers are required in case of these FPGAs to deploy these DSP blocks. So the multipliers also are introduced, RAM for storage, and then microprocessor again, those that power PCs based microprocessors also introduced, and the transceivers, transmitter and receivers were also an added feature in the accumulation age. The ASIC implementations, if you comparing with always this FPGAs were compared with the application specific ICs. If you compare the FPGA with the ASIC implementation, the specific functions were more efficient in case of FPGAs because of the soft logic that IPs were introduced. So, and the platform for this FPGAs, for Xilinx had the high performance blocks of with that vertex 4. So added feature again in the vertex 4 in the accumulation age. So there is a trade off between the unused block and the wasted area. So the unused blocks were not a concern again. So it is okay if the block is not introduced. So suppose you give a multiplier to the users, but whether they use this multipliers or not, that is not a concern for the architects or the vendors. So it is okay if the unused blocks are available, or the microprocessor is attached with the FPGAs are used are really needed for the users or not. That is not a concern. So that it's okay if the unused blocks are available in the FPGAs. So, but the design efforts saving have been the prioritized one. So the design, how efficient the design can be would be that was the priority in the case of accumulation age. So the communication was the focus. The communication industry adapted these FPGAs. So the FPGAs were designed for the communication applications or image processing applications. So mainly in the communication applications, the focus was that they become the data routing engines for communication. So the data, how much more data can be transmitted and received through this and using this FPGAs. So data routing engines were deployed. Also the Cisco used this Ethernet and the throughput, increased the throughput of the switches and routers using the FPGAs. So the FPGAs were used for these communication purposes. Cisco actually used that Also, the new network architectures and algorithms have been developed because of their communication. It was capturing the communication industry. The FPGAs were more popular in the communication industry. So, the features are this IOs had become, because of in the communication we need to be this high speed. Again, there was the change in the I speed, that is high speed IOs have been introduced. Wide data paths are another features. Also deep pipelining. So, the pipelining always enables that wider data transmission. So, the deeper pipelines of the large data communications were also a feature of this FPGAs in the accumulation. So, the communication industry, according to the communication industry, these features were added in the FPGAs. So, the market share is this communication, it grew over half of the FPGA business. So, it is more benefitable in that in the FPGA business during that accumulation age in the communication industry. So, the design tools, which were just the automated and established EDA tools in the expansion age. In case of accumulation age, these design tools introduced some soft logic libraries. More and more libraries have been introduced. That is, the Xilinx, as I told, come up with the microblaze, and Altera with the NIAS, and there are memory controllers and protocol stacks introduced in the design tools and the soft logic ones. So, this design efforts for complex functions have been reduced. So, these are all directly included in the FPGA. So, there is not much, the particular important functions can be designed easily using these soft logic libraries using the design tools. If we take these design tools, the Xilinx has introduced the system generator. Also, Altera used the DSP builder for DSP systems. So, the DSP systems can be deployed easily in the FPGAs. So, how this part of DSP systems introduced in the FPGAs, the system generator is a tool again. So, which is like the MATLAB Simulink tool the Xilinx has introduced, which can be installed with the Simulink, and you will have the libraries like Simulink blocks. So, that this can be pick and place in your program, and the system generator, Xilinx system generator allows the programs to be included like a pick and place blocks, and then connect it, those blocks can be connected to your DSP program. Suppose for a filter design, it can be connected, or it can be a simple digital circuit of a combinational circuit, or the sequential circuit. The blocks which are necessary, suppose the delays or the multipliers or the adders, will be placed in the libraries. And this, not only these components, it has the clock, and it has the compiler, and all are available as libraries in the blocks, in the form of blocks, like any Simulink block, and the connecting it and then compile it in the MATLAB Simulink environment only. That is, DSP systems can be designed in the MATLAB Simulink environment, like the Simulink has the DSP toolbox. So, the Xilinx has introduced this system generator toolbox, and the program can be compiled, and corresponding VHDL or the Verilog code can be generated through this system generator, and that code can be deployed into the FPGA. So, here there is no direct writing of HDL, that is hardware description language for your design, but we can use that the Simulink environment for designing the filter or the DSP systems. So, similarly, Altera also introduced the third party tool with the MATLAB and Simulink, that is called the DSP builder. So, the DSP builder, the blocks, again the library which can be installed with the Simulink. So, if you install it, the Simulink library will appear in the as a toolbox in the Simulink, and with those DSP builder blocks can be pick and place for your design, and then those can be connected. There is again a compiler, clocking, and if you want even the analog to digital converters and digital to analog converter, the boards which are with the daughter cards also available or can be integrated with this DSP builder, or the usage of DSP builder can enable you to code it in the MATLAB Simulink environment, the DSP systems, and then that is compiled and the equivalent HDL code, Verilog or VHDL codes can be generated and in the Simulink MATLAB Simulink environment and downloaded into the FPGA. So there is a synthesizer tool available for both the cases in the Simulink system, in the system generator, also in the DSP builder. So there is a synthesizer involved. Altera in the synthesizer is the Quartus 2 synthesizer, which converts the blocks of Simulink nature, that is DSP builder blocks, into the code Verilog or VHDL. So this is for the DSP systems. Applicable. So the design tools has come up with the new tools or the libraries with the third party tools, we can call them as the system generator and the the DSP builder for DSP systems. So this enabled the deployment of DSP systems in the FPGA easy, made it easy. So in this course also we will be doing this system generator and DSP builder environment codings and developing DSP system using this and deploying in the FPGAs as well. So apart from that, Xilinx has also given for microprocessor usage along with the FPGAs, it has developed embedded design kits. The Xilinx has called that as EDK, whereas Ultra called this as ESDK, that is for microprocessor systems, embedded system design kit, that is the ESDK in the Ultra. So these are for microprocessor systems. And for the DSP systems, so design tools were configured or are improved in the way of having the another tools. Those are the system generator, DSP builder, EDK and ESDK for the FPGAs. So with that we have seen this age of invention, expansion and accumulation. So accumulation added more features and the soft logics and the more dedicated blocks to the FPGAs, and the third party tools have been introduced in the design tools, that is in the integrated design suites also having these third party tools. In the current age, what is happening with the FPGAs? So the FPGAs become programmable with SoCs, that is system on chip devices. Complete system can be deployed into the FPGA. So, the FPGA can be made as a programmable system on chip devices. So, it is evolved like a programmable system on chip devices recently, and there is a complete shift in the FPGA evolution, that it becomes not only the digital circuits. Yes, it is programmable for digital circuit, but the whole system can be deployed into the FPGAs, that is the system on chip devices. So, for example, the case of Xilinx Zinc has the capability of deploying the whole system. Also, the Ultra has the SoC FPGA. Actel has come up, Actel or Microsemi M1 has also come up with the devices. So, even these days this AI modules can be integrated with these boards. The Xilinx has come up with this evolution of those boards. The features are this: it is not only hardware programmable, these FPGAs, as we started with a generic FPGA architecture that is hardware programmable, now it is becoming the software programmable also. So, the feature of software programmable is also added in the FPGAs. So, the full software ecosystems like OS and compilers and middle software also can be supported with the FPGAs. So, the mixed signal interfaces, analog and digital interfaces also can be supported. The IOs can modernize to have these interfaces. So, we have the daughter cards for the analog to digital converter, integration with the FPGAs, and the power controls. Also, the security has been, when the bit streaming is done, when you deploy the code in the FPGA, there is security again is a matter. So, the cryptography has been introduced in the programmable SoCs in this age. After this post-Dennard scaling, the end of this mid 2000, the performance and the density, that is, it is slowed down because of the density gains. Okay, so there is a sluggish performance in this. So, the trade-offs between the power and performance was critical one. So, it needs to be always, there is a compromise between this, whether we need the power consumption less or the performance more more. So if you are concentrating on the performance more, there is a trade-off or compromise needs to be done in the power consumption. So this was the critical issue in that time. So the competition was highly between this FPGA with GPUs. The graphic processor units have been introduced. Also the multi-core processors have come up now, and the ASSPs, like these application specific standard products, these are offering easier design. So but still this FPGAs with low cost have to compete with the performance with these GPUs, ASSPs and multi-core processors. So the performance and power consumption, always there is a competition between these processors and the FPGA. So the FPGA architects still working on these aspects. Also the largest systems, if we keep introducing the accumulation age, if we keep introducing the dedicated blocks and the another design tools and so on, so the larger systems, it requires this teams and increasing the costs. So the design complexity is again also the increasing in this duration. So these are the challenges about the current age. So the process technology, if we look into that, we have just given here the graph which is showing the launch year and then the process technology. So in the nanometers, initially in the 1990s, between this 2019, so it is the Vertex Xilinx had this process technology as 180 nanometer. Throughout this age of among these three ages, there was the processing technology improvements. The Vertex E Xilinx and Vertex E2, the Xilinx FPGA, have come with it is reduced to 150 nanometer process technology. So you can see around this is 2001, and in the 2002 the Ultra Statics GX Cyclone. Statics and Cyclone are the Ultra FPGAs, which has come up with 130 nanometer during this in 1 year. And then in 2004, again there is improvement in this process technology. The 90 nanometers FPGAs have come up. This way Xilinx had come up with the Vertex 4, and Cyclone 2 and Statics 2 were the versions of FPGAs from the Altera. In 2005, this is again the GX 19 nanometer. In the 19 nanometer only, they have trying to add the GX transceivers in the Statics 2. That is also another improvement in the FPGA designs. So the resource Statics 3 and Vertex 5 have come with, you see the 65 nanometer technology has been emerged. And the Araya, again, it is from this Intel, the Altera and Altera has been taken over by this Intel. And then the Cyclone 3, 65 nanometer, 90 nanometer and 65 nanometers were available during this time of 2007, the year. So Statics 4 has come up with 40 nanometer process technology in 2008. So the Araya 2 GX with the transceivers facilities, Vertex 6 with 40 nanometer, that is Xilinx, and Cyclone 4 had the 65 nanometer technology. This is only the device. I mean, if you look at the Cyclone, initial was 130, and then it has grown to 90 nanometer technology, and then it has gone up to the 65 nanometer and Cyclone 3 and 4 itself. Okay, so Araya again the 40 nanometer in the 2009, and in 10 again the Altera with the Statics 4 with 28 nanometers, and the Vertex 7 Xilinx also had this 28 nanometer technology, process technology. So there is a heavy competition between these two. This again. So the Araya GX, GT and SX, ST also are this 28 nanometers. Cyclone, these are from the Altera until this 2012. Also from the Altera is 28 nanometers. Now we are in the 14 nanometer and 16 nanometer technologies available with us. Ultra Scale Plus in Vertex, Ultra Scale also in 20 nanometer. These are from the Xilinx, and from Statics Altera there is Statics 10 14 nanometer is available in the current time. So the how this process technology has been reduced from 180 nanometer to the 16 or 14 nanometer we are in. So there is also a 17, the Cyclone 10 LP, the low power devices are also introduced with again with the transceivers 20 nanometer and 65 nanometers. So there is a That is how this has been emerged, that the process technology from 180 nanometer to 14 nanometer. Now this is the trend which is easy to interpret, that when how the transistor sizing are, how the transistors are increasing, I mean how more transistors can be put into this FPGAs. That is that's the curve which is shown over here in the process technology. So here the devices shown were from Xilinx and the Altera. So what about this future FPGAs? So future FPGAs will have these challenges like the slowing Moore's law, the increases the transistor cost. So there are the factor of increase in the transistors, yes, and the cost is also increasing. That is the one challenge, and we will have this need of usability to compete with the compete with GPUs and ASSP. So FPGAs needs to compete with this GPUs these days. So it is more adaptive to this AI or image processing systems also can be future FPGAs. These are already, we need to compete with this multi-core processors, GPUs and ASSP. The FPGA needs to compete. Sorry. And then what are the opportunities for the FPGAs, how we can improve in these cases. So as it is done in the invention age, so architectural innovation is necessary in the future FPGAs also. So that can give the better architecture. Okay. So this efficiency would increase, and the area minimization, that is also part of this invention age, that needs to be again regaining its phase. And then the design tools, it is not only soft logic and the third party tools, the DSP system deployment, it should also support with high level synthesis. Okay. So from the C and OpenCL, so the C, if we write this code in the C, and again this design tools must be synthesizing that to Verilog or VHDL codes, and even the OpenCL also is the the competition to be done with this synthesis should incorporate C and OpenCL. So the integration of continued integration of dedicated blocks were also the other opportunity to be in the future FPGAs. It is not only this dedicated blocks, so like this all DSP systems, this FFTs as IPs, and all DSP algorithms as IPs been introduced. So it's more and more dedicated blocks to be integrated with the FPGAs, so that this would give the future FPGAs more beneficial to handle the design, especially the DSP designs. So what would be the in the technology review, we have seen that this age of invention, which was mainly architectural invention, that is innovations in the architecture, and the cost containment was an issue in the case of invention age. But in the expansion age, the growth was driven by Moore's law, increased device capacity, and the automation was critical. It was just initiated in the invention age, and it is expanded during this expansion. And the accumulation had the soft logic, that is dedicated blocks, and the communication was the focus in the accumulation age. So current age is completely with programmable SoCs, so that the system on chip device dedicated systems can be developed, and increased design complexity also. This is about this increases obviously the design complexity. The future will be the architecture innovations are required, and the more integration of this design tools should have this high level synthesis. Also the integration of these tools will be the future one. So the technology, the 3 ages of technology gives the overview of how this process technology, especially from 180 nanometer to 14 nanometer changes, and the LUT growth, wire growth, and more features were added. Sometimes area is considered to be a trade-off. Those were still, and those were the review of this technology. But the programmable SoCs are the current age which more architecture innovations are required. So thank you.